Okay, so today in class we talked about empirical formulas, and just a quick review. An empirical formula is the simplest or reduced ratio of the elements in a compound. The procedure we're going to use to calculate an empirical formula is to convert all of our amounts from grams to moles. We want to be in moles. Now the trick, if you're given percentages, just assume you have a 100-gram sample, and then the percentages become grams, and then you just convert those into moles. We'll practice that in a minute here. Once you get the moles, then divide all of these values by the fewest amount of moles. Then we're going to multiply each of these values to arrive at a whole number ratio. For the most part, we're going to have that for most of our examples. Now further, a molecular formula is the actual formula we have in a substance, not the simplified version. Now if we're trying to calculate the molecular formula or discover the molecular formula for a compound, we're going to first find the empirical. Then we're going to divide the empirical molar mass, that's what 2 capital M's usually refers to, from the molecular molar mass. Now this is going to give you a whole number value, which we're going to call a multiplier. And then we're going to multiply all the elements in that substance by that multiplier to discover the molecular formula. Now let's look at this little picture here. What I got here is 2 carbons bonded to 6 hydrogens. And the molecular formula would just be what you see. It'd be C2H6 because we have 2 carbons bonded to 6 hydrogens. The molar mass of that compound would be 30 grams per mole, just adding up the 2 carbons and the 6 hydrogens. The empirical formula for that would be the simplest version, would be CH3. It can be reduced to 1 carbon, 3 hydrogens. And the molar mass of that empirical formula substance would be 15 grams per mole. So let's look at our examples now. Number 1 here, if a sample contains 12.37 grams of calcium and 6.36 grams of phosphorus. I'd probably encourage you to do these practice problems in your journals to give us a little bit more room. So I'm going to work up here. So this is practice 1, number 1. So I have 12.37 grams of calcium and I have 6.36 grams of phosphorus. So let's do step 1 and convert these both to moles. So the molar mass of calcium is 40.08 grams of calcium in 1 mole of calcium. And phosphorus is 30.97 grams of phosphorus in 1 mole of phosphorus. Now when we do these calculations, we end up with 0.309 moles of calcium and 0.205 moles of phosphorus. Now in this compound, we want to then divide these by the fewest. So 205 is our fewest, so we're going to divide each of these values by 205, 0.205, and we get about 1.5 for the calcium, and we get 1 for the phosphorus. Now, we're not going to have too many examples that require too much multiplication here, but I think to get these two whole numbers, we need to multiply them both by 2. So we get 3 and 2. So we then have 3 calciums and 2 phosphorus ions in this formula unit, so I guess we'd have Ca3P2. So 3 and 2. Let's look at the second example. Now circle this one. This one is actually the same calculation we're going to use for our hydrate lab. So if a magnesium carbonate hydrate is heated and the mass changes from 15.67 to 7.58, what's the formula? Now for this problem, we have 7.58 grams of magnesium carbonate. And we notice that it goes down from 15.67 to 7.58. So the mass of the water in the compound must have been that difference, that 8.09 grams of H2O. Okay, now we're going to turn these grams into moles. So the magnesium carbonate, we added up, and it's 84.32 grams per mole. And the H2O is 18.02 grams per mole. When we calculate this out, we get about 0.09 moles of magnesium carbonate, and we get 0.449 moles of water. Now, 0.09 is the least of these values, so let's divide them all by 0.09. And when you're doing a hydrate lab, that compound that goes with the hydrate should always be the lowest value, because the hydrate is what we're going to have a multiplier for here. So this is going to be 1, and this is about 5, so this looks like a 1:5 ratio. So my formula of my compound will then be MgCO3.5H2O. So we're always searching for this value right here, which is our X before our hydrate. Okay, down here for example 3, what is the name of the compound that contains 56.5% potassium, 8.75% carbon, and 34.75% oxygen? I was just told the audio is going to get choppy, so maybe just turn off the sound here and watch. So since we have percentages, let's turn the percentage into a grams out of 100. So let's just say we have 56.5 grams of potassium, 8.75 grams of carbon, and 34.75 grams of oxygen. Let's turn all of these into moles. So 1 mole of potassium is 39.1 grams. 1 mole of carbon is 12.01 grams. And 1 mole of oxygen is 16.00 grams. So we get about 1.45 here, we get about 0.729 here, and we get about 2.17 here. So looking at these three, 0.729 is the least, so let's divide everything by 0.729. This is going to be about 2, this is going to be about 1, this is going to be about 3. So it looks like our compound is going to be K2CO3, and the name of this, going back to the question, what's the name of this compound? Potassium carbonate. So we have a potassium with this polyatomic ion. Okay, one more problem here. If we found a compound that had a molar mass of 146.14 grams, and we had 49% carbon, 6.9% hydrogen, and 43.8% oxygen, what is the molecular formula for the compound? Let's turn those percentages into grams again, so the percent would just be assumed out of 100. So 49.3 grams of carbon, 6.9 grams of hydrogen, and 43.8 grams of oxygen. Let's turn all of these into moles again. So perform the calculation, we get about 4.1 here, we get about 6.83 here, and we get about 2.74. So for these values, the 2.74 is the least of the three, so let's divide everything by 2.74. We get about 1.5 here, get about 2.5, and we get 1. Now for these, since we have the 0.5, we're going to need to multiply everything by 2. So we're going to have C2H5O2 for the empirical formula for the compound. Now this one asks us to find the molecular. So if the empirical is C2H5O2, we add this up, and this is about 73 grams per mole. And it said in the problem that the molecular mass of the compound was about 146 grams per mole. So let's divide the molecular by the empirical, and this means our multiplier is going to be 2. So our molecular compound would be 2 times each of these values. So C4H10O4. Oops, I'm sorry. 1.5 times 2 is 3 carbons. 3 carbons. That stays the same. So this would be C6H10O4. Okay, I hope this helps.